Welcome to the lecture series on mathematical modeling, analysis and applications. In the last lecture, we have discussed the difference between continuous and discrete time levels, and we have just explained the basic definitions of like differential equations and partial differential equations and their linearity and nonlinear properties. And in this lecture, we will discuss about general solution of this ordinary differential equations. So, if we will just go for this solution of this ordinary differential equations, first we will just solve this first order first degree differential equations. Then the methods used for these lectures are like method of separation of variables, and then this homogeneous differential equation form, then linear equations. So, the general form of any first order or first degree ordinary differential equation is represented in the form of like dy by dx equals to f of x y, which involves like one dependent variable as y here, one independent variable x here. In general, it is not easy to solve the ordinary differential equations as given in 12.1, since if it involves like some nonlinear factors or some multiplied factors in terms of f of x y here, then it is not easy to get the solutions. Or if we cannot separate it out x and y in different forms, then it is difficult to get the solutions. There are some methods which are applicable to some particular type of first order first degree equations that we will just discuss here. And the methods are like method of separation of variables, method for homogeneous equations, and Bernoulli equation. This is a special class of equation we have just considered here, and especially these Bernoulli equations are called also method for linear ODEs that can be used in different engineering problems. So, if you will just go for method of separation of variables, so that equation we have just written, that is in the form of dy by dx equals to f of x y. It is not possible to collect all the functions of x and dx on one side, since as I have told that if you will just write a equation that is in the form of dy by dx equals to f of x y, suppose this f of x y term it involves like x cube y plus y square x square plus all other terms, maybe it is multiplied or like x y by x cube plus y cube, then it is not easy to separate this x or y to in a complete sense. And the solution of y and dy, if it cannot be separated in a complete sense, then the variables are, we cannot use like a separation of a variable technique to get the solutions also. So, that is why the restriction is that it is possible to collect all the functions of x and dx on one side and the function of y and dy on the other side, then the variable, and then the variables are said to be separable here. And in this class of problems, we cannot say that we can separate these variables, that is the dx side we can just take all the x variables, dy side we cannot take the y variables. So, that is why if it can be separated, then we can use this variable that is method of separation of variables. And the general form of this equation is like f of y dy, this equals to gx dx here. So, always these methods cannot be applied as I have told for this generalized equation here. So, many times you can just find the difficulty or the problem that you cannot have a solution. Since why we are considering such class of differential equation is that, so in many engineering problems or many like practical application problems or natural phenomena, you can just find that many terms it has been multiplied in a nonlinear sense there. So, that is why it is very difficult to obtain the solution in a complete sense or in a exact sense there. But we are just approaching or we are just starting this process here, that is why we are just considering the simplified methods here. So, first simplified method is the method of separation of variables, where these variables can be separated in a complete form in both the sides. So, if we have just separated these variables of y and x independently, then we can integrate both the sides with respect to their variables, then we can just have a general solution. This means that since Fy dy is involving here. So, we can just integrate this side here, and gx dx that can be integrated that side here. And then we can have like arbitrary constant whenever we will just integrate these difference equations, then we will have arbitrary constants. So, that is why the complete solution, if we will just integrate both the sides with respect to y and x, then the general solution can be written as integration of Fy dy, this equals to integration of gx dx plus the arbitrary constant. So, these constant values that can be depend on this initial conditions or boundary conditions. So, whatever the conditions it has been prescribed to us, accordingly we can determine this constant. So, for this separation of variables, we have just considered a particular example of a difference equation or differential equation, that is as dn by dt equals to kn into C0 minus an here, where all parameters, if you will just see here, other than n are constant here, that is C0, a, k, all are constants. And we have just specified some of the conditions, that is n0 and t0 are the initial levels for like maybe it is population or time or any parameters you can just assume for this differential equation. But for this differential equation, we have just consider here n0 is the population level suppose, and t0 is the time level at the initial level. So, whenever we will just go for the solution of this differential equation here, then as we have discussed, first we will just separate this n variable terms to the left hand side and t variable terms to the right hand side. So, that is why we have just represented this equation, that is in the form of like dn by n C0 minus an, since if you just see here all the terms involved here n variables here, and right hand side we can just keep it as k dt here. Then we have just integrated this one, which is just written as, since n0 is the initial or starting value here, and this is just going up to like any arbitrary n values there. So, that is why we have just written it as like arbitrary n, and t0 is the initial time level here, and t is any arbitrary time level there. So, that is why we have just written integration n0 to n 1 by n into C0 minus an, then integration here, and t0 is the initial time level, and t is any time level we are just going for the calculation here, that is k dt here. And to make this integration possible here, so we have just make these terms as a C0 minus an plus an, we have just added all these terms in the numerator part to get in a complete solution here, and then t0 to t k dt here. And if you will just separate all these terms here, then we can just get that C0 minus an. So, first term it will just get cancelled here. So, that is why we can just write n C0 only. So, C0 is a constant, C0 can be taken out. So, this is n0 to n. So, 1 by n it is there, n dn. So, next term if you will just see here, that is a plus an by n C0 into C0 minus an. So, n will be cancelled it out. So, 1 by C0 it will be taken out, and a is present there, a has been taken out, then n0 to n 1 by C0 minus an into dn. This is a very easy like manipulation of things. So, you can easily get this one, and then t0 to t k dt here. And if you will just integrate this term here, we can just get 1 by C0 log of n by n0 minus your 1 by C0 it is present there. So, log of C0 minus an by C0 minus an0, since your parameters are n0 to n values we are just putting here. Then this one k into t it is coming, t0 to t. So, that is why this upper limit minus lower limit. So, that is t minus t0 it is just there. So, in a combined form if you will just write 1 by C0 log of n by n0 it is there. So, n by n0, and this is in division form. So, that is why this will just come to the upper side here, C0 minus an0 by C0 minus an. This is k into t minus t0. And for the simplicity, if you just consider here the initial time level, suppose from the time level 0 we are just starting here, t equals to 0, then we can just write n by c0 minus an, this is n0 by c0 minus an0 e to the power k c0 t, and we can just write c0 minus an, c0 minus an. So just a reciprocal we are just using, that is we are just using this one, we are just using the reciprocal, that is just we are doing here c0 minus an by n, this is nothing but c0 minus an0 by n0, and it will go down. So that is why it is just written as e to the power minus k c0 t. So this is the statement, only this division we are just using here. So then we can just write c0 by n minus n cancel it out, so minus a, then c0 by n0 minus a, then e to the power minus k c0 t. And since we want to separate n, so which is dependent on time factor here, so we can just write c0 by n as c0 minus a n0 e to the power minus k c0 t plus a n0 by n0 here. So this is the complete solution of n here, where n is the function of time here. And to reduce the number of parameters, suppose if you will just assume here a equals to c0 by a here and gamma equals to k c0. So always we try to reduce these parameters to get it in a compact form. So that is why the complete solution of n of t, which can be written as a n0 by n0 plus a minus n0 e to the power minus gamma t. And this equation 12.5 here, this represent a particular solution to equation 12.4, which is just written as dn by dt equals to kn into c0 minus an here. And if you will just see here, the curve of n of t passes through the point n0 0 here. Since we are just supplying n0 is the initial value for n here, and t0 equals to 0 is the initial value we have supplied. So that is why for that particular values only this curve will pass through n0 and 0 there. So next we will just go for this homogeneous differential equation. The general form of this homogeneous differential equation is that dy by dx equals to f of xy by g of xy, where this function f of xy and g of xy are homogeneous. Homogeneous means we can just say that all terms has the degree same, that is they have same degree with respect to all the variables x and y. So if x and y is multiplied, we can just consider this degree as 2 there. If it is x square y, we can just consider the degree of that term is 3 there. The basic idea of solving this type of differential equation is to convert it into a simple form by substituting y by x equals to v. Since all the terms are homogeneous here, so whatever these terms in terms of y by x, if you will put, then it will just cancel it out. And the idea is that we want to establish this relationship between these two variables y and x in such a fashion that all the terms can be cancelled it out, since it is same degrees are existing for all the terms there. And if you just substitute this term y by x equals to v, then we can just write this y equals to bx here. We are just introducing another variable v, which can be separated it out, since it involves all the product terms that in terms of y and x there. Then we can have like if you will just differentiate y as a vx here, so we can just write dy by dx, since v is also a variable here. So that is why we can just write b into dx by dx, that is 1 here, then plus x into dv by dx. And after this we can just use the method of separation of variables to get the solutions. Sometimes the differential equations are not directly presented in a homogeneous form, then we have to reduce these equations to a homogeneous form if certain constants are involved in that homogeneous equations. So if you will just go for like a example of this homogeneous differential equation here, we can just see that y plus x minus 2, it is not a homogeneous part here, and y minus x minus 4, it is not a homogeneous part here. Since this constants -2 and -4 are present there. If you just see here, degree of this term is 1, degree of this term is 1 here, degree of this term is 1, degree of this term is 1 here. And if you just see here, the degree of this one, it is 0 here, this is 0 here. So that is why this is not a homogeneous form here. And to make it homogeneous, we have to get rid of these constants by substituting. If you just put here, suppose small x is capital X plus h and small y equals to capital Y plus k here, which implies that we can just directly, since h is a constant and k is a constant here, we can just write dx as a dx here and dy as a dy here, where h and k both are constants. And then we can just replace this small y and small x by this capital Y and capital X here. So capital dy by dx, it can be represented as a y plus x plus h plus k minus 2, since we are just replacing directly the variables here. And similarly, this is nothing but y plus k minus x minus h, then minus 4. And now we want to make this h plus k minus 2 equals to 0 and minus h plus k minus 4 equals to 0. If we will just take this constants equals to 0 there, then we can have a homogeneous equation. So if we will just solve these equations like h plus k minus 2 equals to 0 and minus h plus k minus 4 equals to 0, then we will get h equals to minus 1 and k equals to 3 here. And now the differential equation will be reduced in the form of capital dy by dx as y plus x by y minus x, since this part is 0 here, this part is 0 here. To solve this homogeneous equation, now we will just substitute y equals to vx, then we will have here dy by dx as v plus x, we will have like dv by dx here. So then if you will just substitute in that equation, then we can just find it as like we will have this equation that as dy by dx, this equals to y plus x and y minus x there. So directly if you will just substitute here, then v plus x dv by dx, which can be written as y as capital Y, if you will just see here, which can be written as vx here plus x by vx minus x here. So that is why we can just write this one as v plus 1 by v minus 1 here, since x can be taken common here. Now we will have these variables like v and x. So once we will have this equation v plus x dv by dx, this equals to v plus 1 by v minus 1, we can just separate this one, since only one x term it is involved with this one. And we can just write this one as x dv by dx, that is v plus 1 by v minus 1 minus v here. And now we can just add this one here, v plus 1 minus v into v minus 1 by v minus 1. And obviously once you are just getting this is completely v terms here, then we can write dx by x, this is dv by this whole term here. And once we are just putting in this form, that is just coming as like x dv by dx, that is nothing but 1 plus 2b minus b square, this term it will just give you, and this is b minus 1. Then we will just write b minus 1 by 1 plus 2b minus b square into dv, this equals to 1 by x dx plus c. And if you will just take this integration here, then we can just find this one as since we will have like 1 plus 2b minus b square, here we have to multiply it here 2 and divide by 2, then we can have like a minus half log of 1 plus 2b minus b square, this equals to log x plus c. And the complete solution, it is just represented as a log of x square plus 2xy minus y square as minus 2c here. So, once you are just obtaining the solution in terms of capital X and capital Y here, then you can just replace that one. Since we will have like a small x is a capital X plus h and small y equals to capital Y plus k, we can substitute that terms. So, if you just substitute capital X equals to small x minus h, then h is coming as minus 1 there. So, that is why x plus 1 it is coming. Capital Y equals to y minus k. So, that is why k is coming as 3. So, y minus 3, and the final solution you can just obtain if you just put all these variables in this equation here, log of x square plus 2xy minus y square equals to minus 2c. You can just have the solution like x square plus 2xy minus y square minus 4x plus 8y minus 14 equals to c1, where c1 is just given as e to the power minus 2c. This is just a little manipulation. If you just do, you can just get it. So, next we will just go for linear equations. So, the standard form of a linear equation of first order, also sometimes it is called as a Leibniz equation. This is just written in the form of dy by dx plus pxy, this equals to qx. And most of these engineering problems you can just find the equation which is of first order, then that is represented in this form. Since one of this variable y is multiplied with px term and rest of the terms which is free from y terms there. To solve this type of equation, especially this is multiplied by some of these integrating factors. Integrating factors, sometimes it may be e to the power px dx, sometimes may be any factor of x, or sometimes it may be any factor of y. So, many forms of this integrating factors, it has been multiplied with this differential operator to make it in a integral sense factor there. So, whenever we will just multiply these factors with this differential terms there, then it can be integrated easily. So, that is why it is called integrating factors. So, people are using like del m by del y minus del n by del x if the equation is represented in the form of like mxy dx plus nxy dy, this equals to 0. So, many class of integrating factors it can be multiplied to get the solutions. So, either it may be like 1 by mx minus ny, it may be 1 by mx plus ny, or it may be del m by del y minus del n by del x, or it may be like del m by del y plus del n by del x. So, whatever it has been multiplied, accordingly this multiplied factors it will get changed and you will have the solutions. So, mostly these people are using like integrated factor, that is in the form of e to the power px dx for this class of problems. Hence, the final solution it will be, once it will be multiplied, then easily it can be integrable. So, that is why we are just writing here y e to the power px dx. Since it is multiplied with the solution here, then right hand side we can just write it as integration of qx e to the power p dx plus a constant. And some equations can be converted to a standard linear equation form. This equation is called Bernoulli's equation. If you just see here, q of x term, it is just involved with a y power n term here. And if it is just put in this form, then we can just divide y to the power n in the left hand side here, and then we can just reduce another variable y to the power 1 minus n as z. Then we will have like 1 by n minus 1 dz by dx plus pxz as qx there. Since if you will just see here directly, we can just reduce this equation as 1 by y to the power n dy by dx plus px y to the power 1 minus n, this equals to qx. And especially if you will just put y to the power 1 minus n is z, then this is pxz, this is qx, and this will be the reduced factor of z there. And directly if you are just considering one example here, x dy by dx plus y equals to x to the power 3 and y to the power 6. This equation is neither in the Leibniz form nor in the Bernoulli's form here. We have to reduce into the Bernoulli's form by divide the whole equation by x and then convert it into Leibniz form, substituting z equals to y to the power minus 5 here. Which means that we can just write this equation as a dz by dx equals to minus 5 y to the power minus 6 dy by dx here. And the simplified linear equation will be like dz by dx here minus 5, then z by x here, this equals to minus 5x square. Since all these variables it has been kept there, so directly you can just substitute. And the integrating factor of last equation, since it is just reduced into Leibniz form here, then if you will just see here, this is written as a pxy, this equals to qx. So that is why you can just write this one as e to the power minus 5 by x into dx, it is the integrating factor, and which gives you 1 by x to the power 5 is the integrating factor. And the solution, it can be written as z into 1 by x to the power 5 integration of minus 5 x square into 1 by x to the power 5 in dx plus c, and the solution it will just converted as y to the power minus 5 x to the power minus 5, this is minus 5 x to the minus 2 by minus 2 plus c. In this lecture we have discussed about the methods to solve the first order first degree differential equation, method of separation of variables, homogeneous and reducible to homogeneous differential equation, linear equation. Thank you for listening this lecture.